is 2.2. So go ahead and in your packet, turn to page 5. Now, just fair warning, despite the size of the packet, this unit is actually very short. The packet's just really long because there's a lot of figures in it, big pictures. All right. So in reality, I'm predicting we will finish this unit this week. There's literally like in this unit, there's like 5 sections for congruent triangles. The rest is similarity, which we'll do in the next unit. So I'm assuming we'll test by next Tuesday. All right. So first off, just some more general triangle stuff. So another thing you got to know about triangles is how to classify them. There are 3 main types of triangles: scalene, isosceles, equilateral. Those are the 3 main classifications. Now, you can then classify them further by the type of angles within the triangle. So scalene, isosceles, equilateral deals with its sides. Acute, right, obtuse deals with its angles. So typically when you name a triangle, you name it by the type of angles and then the general type of triangle. So like an acute, scalene, and a right isosceles, et cetera, et cetera. All right. So let's start with the side lengths first, because that's probably the easiest way to look at it. So scalene. Anyone remember what's true about the sides of a scalene triangle? Elizabeth. Right. None of them are congruent. They're all different side lengths. So scalene, different side and angle measures, if you want to look at it like that. What about isosceles? Anyone remember what's true about isosceles? Fisher?
2 of the sides are the same length.
2 sides are congruent. So there's 2 congruent sides as well as 2 congruent angles. So congruency kind of goes hand in hand with sides and angles. If there's no congruent sides, then there's definitely no congruent angles. If there's 2 congruent sides, there's 2 congruent angles, and so on and so forth. They just kind of go hand in hand together. What about an equilateral triangle? All sides are equal. And all angles are equal. So all sides are congruent. All angles are congruent. By the way, the symbol that I'm drawing, the little equal sign with a squiggle over the top, that is the geometric symbol for congruent, which you will see a lot within this unit and the next unit. Because math people, we shorthand a lot of stuff. We don't like writing words if we can help it. Now, what's also true about an equilateral triangle? So we know all the angles are congruent. So if all the angles are congruent, what's the only angle measure that all angles can be?
60 degrees.
60 degrees. How'd you get that?
Because 100. A triangle is 180 degrees.
Right.
3 sides.
Right. So every triangle is 180 degrees. If all angles have to be congruent, that means you just divide 180 by 3. That's 60. All right. So when it comes to angles, equilateral, all angles are congruent and equal 60 degrees. So if I ever ask you what the measure of an angle is, and you know for a fact it's an equilateral triangle, there should be no calculation involved. It's 60 degrees. Now, equilateral triangles are the only triangles that you can just flat out say equilateral. You don't need to add acute, right, or obtuse to it, because equilateral is just equilateral. All right. If you want to get fancy with it, I guess an equilateral triangle will always be an acute triangle because 60-degree angles are acute. But whenever you say equilateral, you literally just say equilateral. So you don't have to say equilateral, equilateral. It's just the Department of Redundancy department. Now, acute angle. What do I mean by acute? Less than 90 degrees. So in other words, in an acute triangle, all three angles are less than 90 degrees or acute. Right triangle. So in a right triangle, we know right means 90 degrees. How many right angles have you ever seen in a right triangle? One. And that is consistent. Why can you not have more than one right angle in a triangle? 90 plus 90 is 180. So if you have two right angles, you already hit 180 right there. There's no way you can get a third angle in there and still be considered a triangle. All right. So right triangle only has one right angle. And again, that means it's equal to 90 degrees. Obtuse. What does it mean to be obtuse? One angle greater than 90 degrees. Why can it only be one? Right. If you have two angles over 90, it's probably going to go past 180 just with those two angles alone. So, scalene and isosceles can be described by any of these angles. So you can have an acute scalene, a right scalene, an obtuse scalene. You can have an acute isosceles, a right isosceles, or an obtuse isosceles. All right, all three of those options are possible. Equilateral is the only one that's weird. Now, just to kind of reiterate these theorems. So, triangle sum theorem just states all interior angles add to 180 degrees in a triangle. So, if I drew a diagram, it's called this angle 1, angle 2, angle 3. Remember, interior means what? Inside the triangle. So, that means angle 1 plus angle 2 plus angle 3 is equal to 180 degrees. You guys have been learning that one since probably late elementary school. All right. Now, exterior angle theorem is probably the new one to you. So, exterior angle theorem states that the sum of the the exterior angle is equal to the sum of the non-adjacent interior angles of the exterior angle. So whichever two angles are not adjacent to the exterior angle, the sum of those two angles will equal to whatever the degree of the exterior angle is. So typically what that looks like, you typically have a triangle with an extended line. Let's call this angle 1, 2, 3, and 4. So we know 4 is the exterior angle. Which two angles are the non-adjacent angle? 1 and 2. So these are the non-adjacent. So that means that the measure of angle 1 plus the measure of angle 2 is equal to the measure of angle 4. Now, this does not go along with the theorem per se, but another thing to note is that the adjacent angle to the exterior angle is still supplementary. So angle 3 plus angle 4 is equal to 180 degrees. That's always true as well. So just something to note. The reason I say it is because you may see a problem like that where it may look like an exterior angle theorem, but in reality, you're just doing a supplementary problem. Now, the last theorem, third angles theorem, this one is very, very similar to the triangle sum theorem. It's kind of like the reverse of the triangle sum theorem. All it states is that if two interior angles of a triangle are known, then we can find the third angle. Now, another corollary of this, when we get to congruent triangles, the third angles theorem, is that if two triangles have two sets of congruent angles, meaning that if you had two triangles, you have one set of congruent angles and then another set of angles are congruent. So in other words, you have two pairs of congruent angles. Then the third set of angles are congruent. So, for example, going with what's in the red, let's say I knew what angle 1 and 2 were, but I didn't know what 3 was. So I didn't know what 3 was. I can do 180 minus the measure of angle 1 minus the measure of angle 2, and that gives me angle 3. Now, let's say that I had two different triangles. Let's call this 1, 2, 3, 4, 5, 6. Now, let's say angle 1 and angle 4 are congruent, and we knew that, and angle 2 and 5 are congruent. So angle 1 is congruent to angle 4, and angle 2 is congruent to angle 5. Automatically, if you have two sets of congruent angles between two triangles, that means that that third set, so angle 3 and angle 6, are also congruent. Now, if you look closely, because I know it's a bit thick, if you notice, I'm marking the angles with different ticks. So like 1 and 4 only have one angle, 2 and 5 have 2, 3 and 6 have 3. The reason for that is in math, when it comes to marking congruency with any type of ticks, you can tell which one's which by the number. It's a matching game. All right, so if you have 2 ticks, you match it with the other one that has 2 ticks. If you have 3, you match it with the other one that has 3. If you have 4, you match it with the other one that has 4. All right, and that goes for both angles and sides. It even goes for when you get to parallel. All right, so knowing what we know now, let's see if we can classify us some triangles. So look at the first example. Just from looking at it, do we have enough information to classify this triangle? I wouldn't assume. I would find that missing angle first. Because remember, not all diagrams are drawn to scale. You can't just eyeball them. All right. So how do I find that missing angle of that first triangle? Abe.
You take 180 and you subtract 89.
Right. So what's 180 minus 89? What's 180 minus 89 minus 30?
60.
Be 61. Now, if you have 3 non-congruent angles, you automatically have 3 non-congruent sides. Remember, they go hand in hand. So how would I classify this triangle? It's an acute, because all the angles are acute. It's an acute what? Scaling, because none of the sides are congruent. What about the next one? Do I have enough info? Yeah. How would I classify this one? A right scaling, because we have the right angle marked already. So automatically, if you see a right angle, you don't have to do any other calculations with angles. It's a right, and all the sides are marked, so it's scaling. What about this next one? Yeah, we got enough info. How would you classify it? It's obtuse because we have that one obtuse angle. So if you automatically see one obtuse angle, you can classify that. And then we have 2 congruent sides. So here and here are the congruent sides because they have the matching 1 tick mark. All right. So remember, when it comes to ticks, or not like the animal tick, I don't know why my brain went there, but when it comes to tick marks, it's a matching game. If they match the number on each individual piece, that means they're congruent. So there's 1 tick on 2 different sides, that means they're congruent. What about the last one? That one's just automatically equilateral because all 3 sides are congruent, which we can then conclude that all 3 angles are congruent. Now, let's see how well you can perform these theorems. So, I love triangle problems like this for the sheer fact that, to me, they're one big puzzle. All right? There's not always a direct path to find the angle that you want. You kind of have to work your way around it. All right? So, for example, we're finding this angle right here. So, it's an exterior angle, but just from looking at the triangle it's connected to, we don't have enough information to get there yet. All right? But we can work our way around this diagram to get enough information. So the hardest thing about these is just figuring out where to start. So looking at all the angles that they did give us, which angle measure could possibly give us something that we can get another angle from it? 45. Why do you guys think 45? So I could see it as 180 for the sheer fact if you're looking at this angle. All right, because then that's an exterior angle. You can use that to find this angle, which is another 180. But what I was going for is more the vertical. So these 2 angles are vertical, meaning they're what? Congruent. So that's 45 degrees. Now, that angle gives me enough to find the other angle of this triangle. So right here. Because now I have 2 angles within the triangle. So how do I find it? Right. Take 180, subtract 45 and 60. So what's 180 minus 45 minus 60? 75. Now, this is where I can get a little dicey. So, if we look at this next graph, my idea is to probably get this angle next. So that'll connect us to the triangle we're trying to get our answer from. How does that pink angle connect to the green angle? Right. So, we're on a straight line. If you have angles that are all on that straight line, meaning the vertex is on the straight line, they share that vertex, which they do right here. So they're all on that straight line and they share that vertex. That means they're supplementary. All right, so all three of those angles together will add to 180. So if you subtract 180 from 75 and 68, you'll get the pink angle, which would be what? 37 degrees. Now we got enough information to find that exterior angle. How do I find it?
100 plus.
Add these two together, and that'll equal this angle. So what's the angle measure? 137 degrees. So again, that's the thing with some geometry problems like this. There's sometimes no direct way to get there. So there's no way I could have just automatically in one step got in the angle that I wanted. All right. I had to kind of work my way to it. It's almost like following a map. You got to kind of map your way to where you want to go. All right. Now, let's see if we can solve this challenge problem here. So just from looking at this problem, what theorem do you think we're going to be using? Exterior angle theorem. So we got the two non-adjacent, and then we got the exterior angle. So how would I set this up? So what equal to each other?
8x plus 3x squared minus 6x and 2x squared plus 3x plus 6.
So 3x squared minus 6x plus 8x. You're going to add these two together. Set them equal to the exterior angle. Now, we got to do some cleaning up. So we got to combine like terms on both sides individually first. This will be 3x squared plus 2x. Now, this is clearly a quadratic. So, if this is a quadratic, what do we have to get one side? How do we solve it? You got this is review from Math 1. Right, I got to get one side equal to 0. So, I would recommend moving this side because you don't want to deal with a negative x squared. So, I want to subtract the 2x squared to the 3x squared, the 3x to the 2x, and I'm just going to bring the negative 6 over. So this would be x squared minus x minus 6 is equal to 0. Now, someone besides Riley. How do I solve this? That's probably the easiest way.
Start with moving the 6.
Nope. We can't do anything because of that x. Now, if it was just the x squared and the 6, that's plausible. We can't do anything because of the x. Riley, I know you know. Oh, I guess. So, we can't move the 6 because then we got to deal with the x.
Figure out the x squared.
Nope.
Was it 5 factors of negative 6 by 8?
Close. You're on the right track. Keyword factor. We can solve this by factoring. So we can solve this by factoring. And you guys might want to get used to it. We got a whole unit on quadratics. All right. So if I do big X, who remembers what goes in big X? Okay, so technically it's A times C, B. You need two numbers that multiply to A times C, add to B. So this is A, B, and C, and I'm talking about the coefficients. So 1, -1, -6. So what's A times C?
4.
-6. What is B? -1. So what are two numbers that will multiply to -6 but add to -1? 2 and -3. Now, since our A value is 1, we can just write it as our factor. So this will be x minus 3 times x plus 2, still equal to 0. All right. Now, what's my next step? Someone who has not talked yet today. So now I'm at the precipice of... Can't combine like terms because if I do, because technically we're multiplying them. All right, go for it, Fisher.
Isn't it like remove the negative one?
Not necessarily. Well, not yet, anyway. All right, Riley, go for it. Right. So you would set these both equal to 0 separately. They're like two little mini equations. And then you would solve for x. So x is equal to 3, x is equal to -2. Now, we're not quite done yet because we need to check to see and make sure that there's nothing weird. So we don't automatically want to throw out the negative because if we plug it back in for x, it may still give us a positive angle measure. All right, but we got to make sure that's true for all angles. Which angle measure that contains an x do you think will be the one that will get affected by that negative and it'll remain negative? Definitely the top one. All right, because all we're doing here is multiplying. We're not adding anything afterwards. All right, so that means once we multiply a positive to a negative, it's going to remain negative. So -2 times 8 is -16. We cannot have a negative angle. Well, you can't have a negative angle yet. So, and by yet, I mean when you get to math 3, you will discover negative angles, but in a different context. In a geometric context, there's no negative angles. Yeah. You could do that too, but big X kind of tells you how to do the box method. So box is more for when you're multiplying it back, but you can use big X to do a reverse box. So like you still got to get down to the 2 and the -3, but this could be x squared minus 3x plus 2x minus 6. So you know x times x is equal to x squared. And then from there, it's just x times -3 has to be -3x. X times +2 is 2x, still gets our factors. But the big X, all big X does is get you these two numbers. So it's just like a way to organize that thought process. All right. So X in this case is equal to 3, and it has to only equal 3. So in this case, X equals -2 is an extraneous solution, which extraneous is just a fancy name for we found it. Algebraically, it makes sense, but when you plug that sucker back in, mathematically, it doesn't make sense. Because again, if we plug -2 back into this angle, we get a negative angle, which we know in terms of geometry, especially with triangles, you can't have a negative angle. All right. Now, that was just something to kind of get your brain pumping. If this was on the test, it'd probably be more of like a bonus question, just to kind of get you thinking about it. We'll do more with quadratics in unit 3 and 4. So, isosceles triangles. So when it comes to isosceles triangles, there's also some theorems that go along with it. So remember, isosceles triangles is two congruent sides and angles. So, just so you know, the two congruent sides are called the legs. So these two congruent sides, this is a leg, this is a leg. The third side is called the base. So the non-congruent side is called the base. So this side right here is the base. The angle opposite the base, what do I mean by opposite? It's on the other side of the triangle, so diagonally. So in other words, it's not made up of said side. So if the angle is made up of that side, it's not the opposite angle. It almost looks like the tip of the cone. That's another way you can think about it. So like if you flip this upside down, here's your ice cream, there's the tip of your cone. Or you can think about it as like a party horn, where you put your mouth on, that's the opposite angle. So this angle right here will be your vertex angle. Now, the angles opposite the congruent sides are known as the base angles. And they're called the base angles because the base side is one of the sides that makes up those angles. So these two angles, which I'm going to mark them as, are known as the base angles. And again, the reason is they're adjacent to the base. One of the sides that make up those two angles is the base. So here's the question. If a triangle has two congruent sides, does it automatically have two congruent angles? Oh, it definitely does. All right. It's more so about, specifically in a triangle, that's true. Not necessarily in other shapes, but in triangles, that's true. Because if you think about it, all right, if you have two congruent sides, no matter where you place those congruent sides, they're always going to be connected in some shape or form. So like they could be here, they could be here, or they could be here. All right. But no matter how you put it, the distance between the edges of those two sides, not where they meet, but the edges, will always have a very specific length. All right. Now, because of that length, that means that if you connect that side to one of the congruent sides, it cuts the same angle. Now, there are ways we can actually construct that and you can see it a little bit better, but that involves pulling out compasses and doing a bunch of stuff with circles, and we just don't have time for that. All right. But mathematically speaking and logically speaking, it actually is true. Like if you go into construction or engineering, you will see that that's always going to be a fact. The sides are congruent, the angles will be congruent in a triangle. So, let's talk the isosceles triangle theorem. And all it states is, if you have two sides of a triangle that are congruent, then the angles opposite, sorry, I'm writing it up here because I don't have enough space, opposite the sides are also congruent. So, for example, RT is congruent to RS. So that means that angle T, because that's opposite RS, is congruent to angle S, which is opposite of RT. Now, the converse of the isosceles triangle theorem is easy. It's just basically the reverse of what we just said. So if two angles of a triangle are congruent, then the sides opposite those angles are congruent. So since N and M are congruent, that means LM, which is opposite angle N, and LN, which is opposite angle M, are also congruent. Now, why is that important? This is when we use it to solve for things. All right, so occasionally you will be thrown an isosceles triangle where you have to solve for x or solve for an angle. All right. Now, they kind of already set this one up for us. So, they want us to find angle E. So, they want us to find angle E in triangle DEF. Angle E is right here. Now, they already said that angle D is congruent to angle E. Is that true? So if you look at the picture, Can we tell for a fact that that's true? Yeah, why? Because they're opposite the congruent sides. Since they're opposite the congruent sides, they're automatically equal to each other. That's a known fact.
Then can we automatically solve the problem?
Yeah, you can go ahead and solve for x. So, if we know they're equal to each other, that means we're going to set what's their angles are what? Equal to each other. So they already set it up for us. So 5x is equal to 3x plus 14. So, doesn't matter how you do this, but I'm going to subtract 3x over. Get 2x is equal to 14. So what's x equal to? 7. Now, that's not what they asked us to find. What did they ask us to find? They want the angle measure of E. Now, we could simply plug the x value back in for E and evaluate that. But we could also do what? Multiply 7 by 5 because we know that D is congruent to E. All right? So sometimes, if you know they're congruent, pick the easier function. All right? So just for funsies, I'll do both. So angle E is equal to 3 times 7 plus 14. 3 times 7 is 21 plus 14. That's 35 degrees. Now, it never hurts to always check to make sure you got the right thing. So you should get the same answer when you plug in for x. So if I do that, I get 5 times 7, which is in fact 35 degrees. Now, that one was a fairly easy one. Crap. So let's look at one that's not necessarily the easiest. This one's not too bad, but it takes a little thinking. Look at the next page, number 1. What angle did they give us? They gave us the vertex angle. How do you know it's the vertex? It's not opposite one of the congruent sides. So these are the two congruent angles. So they gave us the vertex. Now, here's my question. They want us to find angle C. So that's what we're trying to find. How do you think I can find that angle? Let's go, Ayla. Good. And why did you divide by 2? Right. So since these angles equal the same thing, that means if we just take 180 and subtract 78 to it, which should give us 102. All right. That means that the sum of these two angles equal 102 degrees. Well, since they're congruent, that means that we have to cut that angle or that angle measure in half, or that sum in half, however you want to put it. Because think about it. If I told you the two angles equal to 12, but they're congruent, what would the two measures have to be? 6. All right, because 6 plus 6 is 12. So I'm going to divide 102 by 2 and get what? 51 degrees. All right. Number 3 looks very, very similar to the one we did previously, so I'm going to skip that one for now. All right. Now, moving on to equilateral triangles. So there are 2 corollaries when it comes to equilateral triangles. There's equilateral triangle corollary, which just states that if a triangle is equilateral, it is also equal angular. So technically speaking, equilateral means all sides congruent. Equal angular means all angles congruent. All right, if you're in Mr. McGinn's Latin class, those roots, you know. All right. So, on the opposite end, equal angular corollary is if a triangle is equal angular, it's automatically equilateral. Say it again.
All the angles are equal plus and would already be equilateral.
Yeah, exactly. Well, sometimes what they do is that they will mark a triangle like this. So they only mark the angles, but they didn't mark the sides. So what they're saying is this is a part of math is logic. All right. So logically speaking, if this is true, this must also be true. All right. So what I'm saying is that if all three angles are congruent, then it must also be true that the sides are congruent. All right. If you ever take college math and you take a logic class, you'll learn about what's called if and then statements. And they get pretty interesting. So all it's saying is that if we know that these three angles are congruent, that means all three sides are congruent, and vice versa. If they told us all three sides were congruent, automatically that means all three angles are congruent. So it may sound, so I see what you're saying. It may sound silly. It may sound like, oh, that's obvious. But in mathematics, a lot of times having that logic in math, the thing I like to say is we cannot assume anything until we prove otherwise. All right. So you know how in courts like innocent until proven guilty? This triangle is innocent of not being equilateral until I prove that it is. All right. Which part of this unit is proofs? All right. So in other words, a big part of this unit that we're going to be doing is actually proving that two triangles are congruent, even if they may look like to the naked eye that they are. But we don't know for sure. We can't say otherwise until we have enough information to prove. So a big part of math is actually gathering the evidence using logic and just mathematical reasoning to show that these things are true. Yeah. So does that make a little bit more sense? All right. So we're going to do one of these. So I know that y'all can solve a problem, but I just want to at least get the setup. Okay. So for the first one, number 6, is this an equilateral triangle? So they're asking us to solve for x. What am I setting that expression equal to? 60. Now, you could multiply this expression by 3 and set it equal to 180. But that's more work for you and you're dealing with bigger numbers. The easiest way is we know that every angle in an equilateral triangle is 60 degrees. So we just got to set 2x minus 6 equal to 60. Now, I'm not going to solve that because I know y'all can solve a two-step equation. I just care about the setup right now because that, in my opinion, that's the hardest part. What about 8? What's true about those two sides that they marked? They're equal because all three sides are equal. So if I wanted to solve for mn, what's the first step? Right, solving for y first. So y plus 10 is equal to 4y plus 1. Then from there you solve for y, plug that sucker back in. Any questions on isosceles or equilateral triangles? All right, the last thing, and then we're done. This one's fairly quick. The last theorem that we have is known as mid-segment theorem. So, what is a mid-segment? All right, when you hear the word mid-segment, what are you thinking? It's in the middle of the triangle. Well, middle conditionally. It may not look like it's in the middle of the triangle, but it's formed by two midpoints of the side. All right. So the mid-segment is just a segment that connects the midpoints of two sides of a triangle. So if you found the halfway point of two sides of that triangle and connected those 2 points together, it would form the midsegment. So for example, what they did here, the midpoint of this side would be right here, which you can tell because they marked these two little pieces as congruent. That means that they're half of that side. And they did that to all three sides. So here, here, and here. Those are all midpoints. Now, they're saying that if you take those midpoints and connect them, that gives you the midsegment. So that little segment right here is the midsegment. Now, how many midsegments do you think a triangle can have? 3. So there's 3 midsegments can be formed. So if you connect these two, that's a midsegment. You connect these two, that's a midsegment. If you connect these two, that's a midsegment. Now, why the heck do we care about midsegment? Well, midsegment of a triangle is parallel to the third side and half the length of the third side. So in other words, it's parallel to the side that we didn't get the midpoints from. So it's parallel to the side that does not form it, or that does not contribute to the formation. You want to think of it in terms of real life, it's more like in the cuck chair. All right. You don't know what that is? I'm not explaining it. All right. So, some of you do know what it is. So, basically, it's not the contributor here. It's not contributing to the formation of the midsegments. Richard can explain it to y'all later, apparently.
All right, Rachel, let's hear it.
All right, so now the way that they connect is that not only are they parallel, it's half the length of that other side. So, for example, they're saying that DE is parallel to AB. So this is the mathematics symbol for parallel. This is also the mathematics symbol for parallel as well if it's on the shape. Now, this is another example of tick marks. So you could see this with 1 arrow, you could see it with 2, you could see it with 3. It just depends. Now, that means that this segment right here is half the length of segment AB. So for example, let's say this length was X. That means this length would be 1/2 X. All right. So let's look at this next one together. Let's just state some facts here. So first off, let's name my 3 mid segments. So what are my 3 mid segments of this triangle? So side AB, what else? AC, and segment what? BC. So these 3 segments are my mid segments. I'm just naming them. Now, AB has to be parallel to which side of the triangle? To YZ. So AB is parallel to YZ, which we can mark with 1 arrow. AC has to be parallel to which side? XZ. So that one's parallel. And lastly, BC has to be parallel to which side? XY. So right here. Now do you see where like the multiple tick marks come in handy? Again, it's just a matching game. So since these are arrows, 3 arrows match with 3 arrows, they're parallel to each other. The math we may do is complicated, but the signage is not. Whatever mathematician made this stuff up, they knew it was going to be a pain in the butt already, so they were like, okay, might as well make the actual symbol stuff easy. So, that being said, AB is equal to half of YZ. You could also say that YZ is equal to twice AB. So the reverse is true. You can then say that AC is equal to half XZ and BC is equal to half XY. And again, the reverse is true. So XZ is equal to twice AC and XY is equal to twice BC. Now, why is this important? Well, when you get to mid-segment problems, just make sure that you know that you can interchange these. So if you don't want to deal with a fraction like half, even though a half is a pretty decent fraction, you can always write it in terms of twice instead of half. You just got to reverse it. All right. So, real quickly, look at this example. So they want us to find CD. So this side right here. Automatically, we can find it. What is CD? It's 8. Because we know that XY is twice CD, or CD is equal to half XY. Because CD is the mid-segment, because it's formed by the two midpoints, and it's obvious that these two segments are parallel. What about DF? Yes.
The last one, it should be XC, not XY.
Yeah, you're right. It's the end of the day. My brain's almost shut down. So, how do I find DF? Multiply VU by 2. So 2 times VU will give us DF. So in this case, that's 2 times 9, which is 18. So DF is 18. Now, last thing we're going to do is solving for X. So, again, I know that y'all can solve an equation. I really only care about the setup. Okay? Like, y'all are confident in solving a linear equation, right? There's no square or anything next to the X. Basically, any basic equation is a linear equation, right? For example, that's a quadratic equation. That's an exponential equation. That's a logarithmic equation. See, that's math 3. Have fun with that. All right, so now, knowing what we know, what can we say that we definitely for sure know? RT is equal to double CB. You could also say that CB is equal to half RT. Now, this is that conundrum of where it doesn't matter which of these you use to set up your equation. I say use the one that's doubling because then you're dealing with whole numbers and not fractions. So, I would use this one as your reference. So, using that as my reference, how would I set it up? So we pretty much have the equation. Good. That's all it is. So if you know this, you basically have the equation. You just got to substitute the expressions for each side and plug it in respectively. All right. From there, you're just distributing the 2x and then moving things around and solving for x. So again, in my opinion, the setup is the hardest part. The solving part, that's not that hard. All right. I have full confidence that y'all can solve a basic equation, which that's a basic equation. All right. Any questions on any of these theorems? All right. So you do have a delta math that covers the 2.1 stuff and the 2.2 stuff. It's not too long. I think it's only like 18 problems. I'll give you guys a little bit more time to work on things tomorrow. Delta math due midnight by tomorrow night. So you got you actually got over 24 hours to work on that delta math. Make sure your journal is in that box before you leave, otherwise it's a 0.